Okay, so we're going to take a look at a nice example in Matlab um, where we're going to use autoencoders to try to build a deep neural net. And so the idea is we're going to try to um, classify the digits. Sorry about using this example over and over again, but our data set is going to be the MNES data set um, with some digits that are going to be 28 by 28, and we have 5,000 training examples. Okay, and so let's go ahead and run through these cells here and see what we get. We'll just do this cell by cell here, and so this is just loading up the data. I probably should have cleared the memory out. I was doing a bunch of stuff before too. Well, 5,000 uh, training images could take me a bit to load this into memory. Okay, there we go, and here are some samples. So these are looking pretty familiar. Good. Let me pause for a minute and clear the memory. Okay, so our input dimension is 784 dimensions. That's 28 by 28. And then we're going to step down, I believe, to 10 first. And then we're going to, yeah, 5,000, okay. And then I think we're going to have a deep layer, so we're going to have two or three hidden layers. Let's see how this is going to work. So our first hidden size here, oh, I guess it's 100 first before we go down to 10. Okay, and so this gives you lots of information here. We're going to skip the comments for now and just go right to the autoencoder. Again, our training images, there's well, altogether there was 5,000 images. They're in R784. We're going to go down to R100. Now, in order to train this, there's some special regularizations that are needed, which are some additional additional constraints on what kinds of solutions we're going to get. So L2 weight regularization means that we're going to penalize large weights. Okay, and this is the 0.004 here that you see is going to be the penalty or the weight of the penalty. Sparsity regularization, that means we want our answer to be sparse, meaning lots of zeros. So we're going to have just few weights that are not zero. Sparsity proportion is the number of values that we would like to have small. And this is saying that we're not going to scale the data in this case. And so yeah, let's go ahead and train our autoencoder and see what happens. Oops, I forgot to do the hidden size here. Oh, I guess we need to do this to evaluate that one, evaluate that one. Now we can evaluate this one. Okay, and there's our training, and we have this nice little training tool here. You can watch the training go by. This is kind of nice of the graphical version of the neural net. So we see we're going from 784 to 100, then back out to 784. And so this is training on the identity matrix right now. So this is not training on the classifier yet. This is training on the identity. So X is going in, X is going out. So currently we're at 40 iterations out of 400. So I'm going to put this on pause. And when I come back, you'll be able to see how long it took here because we are tracking time. So I'll be back when it's finished. Alright, so we're back, and that took about 8 minutes. Not too bad. And so, yeah, we can see that the maximum epoch was reached. So we did not reach our performance goal, which was 0. That's pretty low. And our gradient stayed above 1 times 10 to the minus 6 power. And we had no validation checks. Okay, so now what's going to happen? We've got our training done. By the way, at this stage, you could take a look to see what the weights are doing, right? Because here we have weights. The weight matrix here is going to be what, 100 by 784, right? And so each of those rows of the weights represents a 28 by 28 image. And so it's often very interesting to see what that looks like. I think I've got it here in the code. Let's double check. Visualize the weights. Is that going to let us do the right thing? Well, we can sure check. Evaluate selection. So far I don't see anything. I don't see any weights being plotted. Oh, so what happened? Well, that's odd. Let me try it in the command window here. I guess I could say figure 3 plot weights. Autoenc1. Oh, there we go. Good. So this somehow knew that they were 28 by 28. I think we did tag that somewhere initially. And so this is a very interesting picture. Let me see if I can zoom in on that. Because this is telling you what each weight is like going to be tuning into when it's looking at a graph. So if it is, for example, if this first box sees this curve right here, it's going to be active. It's going to put out a strong signal. And if this one was active, it would put out a strong signal. Okay. So these are this is a nice way of kind of at least trying to see what's happening with those weights. You remember from our neural network video at the beginning, they said that this was going to happen, but then they didn't see that in their neural network. But we're actually seeing that coming out very nicely. We're seeing some structure in our weights that you don't normally see. Good. All right. So again, these are visualizing how many weights do we have here? There's 100 of them. And each of these 100 boxes, there's 28 by 28, which is 784. So again, these are the 100 rows of W. Okay, that's what you're looking at here. Good. All right, so that turned out nice. So let's see. The next one we're going to try to encode the next set here. So I'm going to extract the features for my autoencoder, and those are in R10, right? No, R100, sorry. So those are in R100. And so now our next hidden layer is only going to have 50 layers on the hidden layer. And so what we're going to do is we're going to train the autoencoder, but we're going to use those features that we just extracted in R100 as both input and output. Okay. And so it's training again on the identity. And so when I say evaluate current selection, the neural network training box will come up. Here it is. This one's going to go a lot faster. And done. Good. Okay. So now what we're going to do is we're going to paste the neural nets together to go from 784 to 100 to 50. Okay, and then oh, we might be doing one more. Let's see. we've already viewed the autoencoder. We're going to extract these features from this network. So we're going to evaluate that. So this is now giving us a bunch of data in our 50, right? So um, our last extraction gave us data in our 100. Oh, so we are going to do one more training session, and that's the soft max problem. And so what do I mean by that? Let's see, evaluate current selection. So we're going from R50 to R10, and this is where we're actually doing the classification problem. Good. And so by softmax, remember what softmax is? We're picking out the biggest one as the one that um, represents the target, or the output, I should say. And then we're going to match that to the target. All right, so that was very quick. And here we go. Now what we want to do is, what's neat about this is we can now stack these autoencoders. And so we're going to call that the deep net. And the deep net is going to be stacking the autoencoders. And now we can view our deep network. Where'd that go? Let me just copy and paste here. Not sure why the viewer's not working when they did that. Let me get rid of some of these figures. Might be overloading the thing here. Okay, let's see, view our deep net. Done. Okay, here it is. So we're going from 784 to 100 to 50 to 10, and that's our output. Now I should say, why don't, some people will ask, well, why don't we do this right at the beginning? Well, how many parameters is this? This is 784 times 100 times 50 times 10. That's 784 times 100 times 50 times 10. That is 39,200,000 training parameters that you've got there. How many data points do you have? 5,000. So there are a lot of parameters here. And so we need a way of getting those parameters close to a good solution, and the autoencoders will attempt to do that. Okay, so that's the whole purpose behind the autoencoder for a deep network. It does training on the identity, so you don't have to come up with your own inputs and outputs, and also you can train it layer by layer, which is very nice. Alright, so now with the deep network formed, we can do the training. So the idea here is that the training should be fast because we should be very close to a minimum. Where's the training? I guess we haven't started training yet. Oh, that's in the next one. Oh, I guess we're not training. Sometimes we fine-tune the parameters. Oh, I guess that's coming. Oh, we're going to try to use the deep network as is. So let's go ahead and test that. Here's our confusion matrix. Now what we did here was we just glued our autoencoders together and got this as our output. So there's a lot of stuff out here, right? 64, 17, 18, 34. There's a lot of misclassification going on here. So we need to do better than that. And so the way we're going to do better than that is we're going to train the entire network. And so this is what I was meaning before. So let's go ahead and just train the entire network now. And again, Do you see what's happening? We're going from 784 to 10, and it's moving very, very quickly. A lot faster than it did before. Um, well, I think I may. Oop, what happened? Oh, the minimum gradient was reached. Remember what we were talking about with the vanishing gradient problem? This could be part of that. So, um, yeah, because we're multiplying numbers less than 1 together, we could get very, very, very small gradient. And so that's going to be a problem. But let's see how it works in this example. I think because we were pretty close to a minimum anyway, I think it's going to do a good job. So let's go ahead and plot our confusion matrix. Let's see, did we plot our new one? Not yet. So let's plot the confusion matrix for the new system. Okay, so here we are. Ah, there we go. Now we're looking pretty good. Overall classification rate of 98.5. Excellent. Good job. So this again is the stacked neural net. And so you can use autoencoders to train each of these layers separately and then glue them together and then just do some fine tuning at the end. Good. I know I rambled on for a bit, but this was kind of an interesting example of how you would use several neural nets together to get a deep network. And so this is an example of a deep neural net, although it's not too deep. There's really just 2 hidden layers, but it's complicated enough that training would be very, very difficult without using the autoencoders. All right, I'll see you later.